Swayam Prabha. Digital India. Educated India.
So there are minor changes to code that I have done, and we will first go with shared memory through debugger, and then we will look at Unix pipe as an example. The code is very similar to what is already given in the textbook. Only change I have done is put in a sleep here to sort of let debugger and other things come into play. This was not a must. Similarly on consumer, right now I am going with the code that is from the book, but later we will remove this line of code and still observe what happens. I'm using two screens, one with a slightly larger font, the other with a slightly smaller font. So producer I am going to run with a smaller font. The command I have typed is gdb and the binary name. Now when you are debugging, you have to be careful that the compilation has made sure of having debug enabled. So what it really means is either you use a -g gdb and turn off optimization. This is capital O0, no optimization. In past, some of the GDB tools also used debug level 3. So G3 also helps to get additional information for debugging. And then some runtime flags and other things are there for making sure we can use the system calls and so forth. Yes, this is where we are running the producer, and I will run the consumer under debugger here. First command is list or L, just L works. What it does is it shows the lines of code that are there in the file. And if you repeat it again, it will show the next line of code. So first time we are seeing from 17 till 24, then 25 till 30, 33, 34. And let us do one more. Sorry, not an L. So first, so these are all setting up variables within, these are local variables by the way. So the first real line of code that we are going to hit is line 39. So I will put a breakpoint here. Break or B is the short form. And I can just say 39 because we are using only one file of code. This will work. So right now it says on producer line 39, I have put a breakpoint. B is the term I have used. Break could be the full form there. And then I can say run or continue, depending on where we are. So first time you will have to say run or R, and it comes to the breakpoint, does not execute it. It has not executed the breakpoint yet. Fine. So this is where we are going to create a shared memory resource and get a file descriptor. So if I do N, which is next step, it has executed this line and it is going to execute F truncate. I can do an N3, which means run next 3 steps, which is where it's printing message 0. Now for debugging, we can also do some things like print shm_fd. It will print the value of shmfd. To quickly recap, the file descriptors in Unix environment, 0 is standard input, I guess, or standard output. 1 is the other way around, and file descriptor 2 is standard error. And then we have the third file descriptor right now being used as shmfd. It has been mapped and all those things have happened already. Why am I saying it has been mapped? Because when I said N3, we ended up running these lines of code. After open, we have run truncate, we have run mmap, and now we are at sprintf. So if I do N, we have printed the message 0. now we are incrementing the pointer by message zero's string length. So before we do that, let's print the pointer value ptr, and then if I do next and print the pointer value again, it has moved by 9 characters or 9 bytes. What was message 0? I think this piece of code is slightly different. It may be not exactly hello, it may be something else. We can also do print message 0 to know that. Studying with a space at the end. 1, 2, 3, 4, 5, 6, 7, 8, 9 characters, so it has shifted by 9. Which really means it has not gone and included the null termination. Now at this point, if I run my client, right, because of the font size, this is the shared memory client I am running here. Let us just list the next few lines. I will put a breakpoint at mmap, which is line 41. So break at 41. Run it. Right now the pointer is not initialized. When I do n, pointer will be initialized. So I will print ptr. Now should these addresses be the same on both sides? Need not be. Right now they're coming as same, but need not be. It depends on where the spaces are available in the current virtual memory map. Okay, so what are the next set of instructions we will have? We can list. So after 41, where we have printed the map, we are looking at exception handling. That will not happen, so we can just do a next. At line 48, we are going to print whatever we read from pointer. So let us do next again. Next step is actually removing the map. SHM unlink is removing the shared memory that was created here. This is where we had created it with the name. As producers, as a consumer, we are going to remove it. Intentionally, I will terminate right now without removing it. So let me do a quit. Now what happened here was we didn't see the printout because there was no new line here. So I'm going to do a few minor changes to my code and then run it again as a client. As a consumer. What was the break line? Do you remember? So we'll break it. Run. Next. Now this time, because I have put a new line, the printout is coming to us studying. Remember, we had only printed message 0. Again, I will quit. Out on the producer side, I will allow it to run. Okay, so to let it run, I will say continue with execution C. It will write the rest of the message, sleep and exit finally. Now when I run the consumer again, 41, run, next. What should it print now? Any thoughts? So we have finished all these things. That's why all the three messages 0, 1 and 2 should show up now. So studying operating systems is fun is what shows up. Now there were a few things I wanted you to look at as we were debugging. One, by terminating my debug session, I could avoid running some part of the code. The cleanup was not being done. This SHM unlink was not happening, which demonstrated that if multiple simultaneous invocations of consumer happens, probably they will read overlapping parts, and the first one that will end up removing, subsequently any consumer that comes up will have an error. So if I say continue now, it exited, I can rerun it or I can quit and then come back. If I just say break at 41 again, let us do that. Run. Now this has exited. Shared memory it could not get. Why did this happen? This is the message we are seeing. When we try to open the memory, remember last execution, we had allowed it to be unlinked. Because it is removed, we can't get to it. I have gone a bit fast with the demonstration, but I would request you guys to try it now by putting breakpoints at different places and exiting or pausing execution. Initially, I only allowed message 0 to be printed, then ran the client. Did not allow the memory to be unlinked. Shared memory was not unlinked. Second time I ran, I had allowed all three to be printed, but I did not allow the shared memory to be unlinked. Third time I allowed shared memory to be unlinked, and then fourth time when I ran it, it ended up printing this error. At systems level, when we are debugging things, when we are designing things, we will have to ensure that we are creating conditions for such errors to surface themselves. This is where you will end up debugging or analyzing root causes or creating race conditions by pausing specific threads or going into corner conditions and so forth. Now there are ways to modify values of the variables themselves. For example, when I was printing a value for pointer or messages, that was read. Debugger allows us to even modify those values. I will not go into those concepts today, but a graphical user interface, you will be able to do a lot more in a simpler manner. So I'm taking a 5-minute pause. I would let you guys run the code for shared memory with producer consumer. And then we move to Unix 5. Again, to recap, as consumer, the primary pieces of code we are looking at is SSM open, mmap. As producer, we are looking at SSM open with create flag, truncate to set a size to the shared memory, and then mmap again. Reads and writes will be happening as if we are accessing memory. So this is just a printf to memory variables. In consumer, we were also doing an SSM unlink. So I'm taking a pause here and letting you guys run it. If you get into issues, we will quickly help troubleshoot so that you are able to proceed further.
So can you again tell
Hi,
where
Abhishek.
is this file? Yes, sorry.
Okay, so the way you will get to this file is Chapter 3.
Yes, sir. Chapter 3. Okay, sir.
Shared memory, POSIX consumer and producer. I didn't want to end up modifying the original code, so I have copied them into a different folder.
Oh, okay, sir.
Similarly, Unix pipe example is what I'm also picking shortly. So these three files from chapter 3 is what we are looking at. Yeah, was there another query?
Yes. Hi, sir. So I was looking for a different question for a different perspective. So yeah, these toy examples I have studied. I mean, many people have studied them before, but it would be really interesting if you could tell about a practical application for these pipes. For real life. For example, can you describe how Chrome uses these ideas to improve synchronization? I mean, what I'm looking for is a more practical or a real life example for these ideas.
Better applied example. Yes. In fact, the bakery algorithm, as we build up for it, again, I'm not going to give you a thorough intuition on it of an applied aspect, but I will leave you with enough thoughts of seeing how that logically flows into consensus mechanisms, into distributed ledgers and so forth, because we are still talking of a single system coordination of applications. But logically, that bakery algorithm, as we finish discussion today, you will get to appreciate how we are looking at just a sequence numbering as an example, helping other things to happen in a resilient, robust manner. Okay, so coming back to message passing using shared memory. So again, shared memory is one of the things, as I said during the pre-break session, a lot of onus on the application to identify the boundaries and make sure coordination happens. So to give an analogy between UDP and TCP, TCP takes most of the complications and makes the application easier. UDP, on the other hand, you have to do a lot more things as part of application or the user space. Similarly, shared memory, you will have to do a lot more work as part of application. So it tends not to be as heavily utilized. What I am seeing more used, and again, this is take it with a bit of salt or whatever you want to do, is today invariably we are using inter-process communications based on inter-network or sort of TCP, IP and similar approaches, because you cannot expect everything to be locally on your machine. So you end up invariably discovering the URLs and accessing them through URLs. So internal libraries may hide the complexity. The application may not directly use shared memory, rather they may use URL or URI based communication. I'm not sure if I gave you the answers directly there, but today's constructs have moved to a next level where you are either using intents or notification APIs supported by the platform rather than directly using these low level constructs of shared memory. But yes, internally they would use these constructs. Sorry, I couldn't see who was the person who was having the question. Was that Adi?
Yes. Yeah, I asked the question. Yeah.
Okay. Yeah, I don't think I gave you the exact answer because the domain where you are going to, even I am not too comfortable there. Okay, so any other questions?
I can try adding a little bit over here.
I mean, it's sorry.
Hello.
Yeah, Vijay, please go ahead.
Yeah. So the idea really is about concurrency as a thinking paradigm for thinking about applications. So when you say that you want to have an example of pipes or IPC, probably the question that you're asking is, how is concurrency helping me to think about my applications or solving my application problem? A simple example, for example, would be email. concurrency allows you to separate the concerns in terms of mail user agent, the front-facing part of email, and the mail transfer agent, the actual email, post office, things like that. So concurrency, separating out the concerns, is something that concurrency helps you to think of, so that you can develop the mail transfer agent software very independently of the mail user agent, and then use IPC to transfer the data from one to the other. So inter-process communication actually is, in some sense, I mean, it's practice. The way you use it is to separate out the concerns in a full application, and thereby separate out the implementations. One sees the protocols from that perspective also. One can possibly see them. So the HTTP and the browser would be the other side, the other examples. In fact, you will have some of it tomorrow, when we will look at networks and see how networking has helped to change or expand the idea of execution.
Right. Yeah, and Adi, I think we will have to get more white box into the browser implementation to discuss applications there. But yes, Abhijat, thanks for bringing a mail application oriented paradigm where the mail daemon or the implementation can have a front end for the user, or say SMTP as a back end and POP3 and other things as a front end, and try to synchronize between them.
Yeah. I mean, and the browser would be much more challenging. You have quite rightly said that. In fact, REST is something that would be discussed a little bit tomorrow. That would help to detail out what are these probably seeking.
Right. Fine. Any other questions? Otherwise, I will move to the next demo. We have 2 more demos, so I want to make sure we are able to wrap up on time.
Thank you for the clarification. Thank you, Abhijat. I think that definitely helped. Thank you.
Okay, so pipes are the other one. Again, probably these are coming when I and Abhijat were discussing. We were talking of Morris Back and similar books that have been published in the 70s. It tends to show that probably we are oldies in that perspective, but I do know for a fact that a lot of POSIX things still have not changed there. So pipes themselves come in 2 flavors. One is named pipes, in which case we do not need a parent-child relationship between who is sending and who is receiving. Or there can be ordinary pipes wherein a parent forks off a child and then child and parent can talk. These ordinary pipes are also the fundamental approach through which on Unix we run commands like this. So if I have to say ls and pipe it to word count, this pipe symbol actually internally redirects the standard output of ls command to standard input of word count and implements it. So this allows even processes with parent-child relationships and so forth to talk to each other. That is ordinary pipes. On the other hand, if we end up taking a pipe under /tmp or some other folders, we can have a named pipe wherein 2 processes can talk to each other without having to worry about a parent-child relationship. So ordinary pipes where we have a sort of parent-child relationship can implement producer-consumer, and typically for a parent, when we create a pipe, there will be 2 file descriptors we get as a return to the pipe call, and a logical protocol has to be built in so that a parent reads at one end and writes to the other end, and child does the vice versa. It gets FD1 as the reading end flipped over, and FD1 of child comes as a reading end to parent. So that relationship we have to make sure that is being properly done. On Windows, there is this implementation also referred to as anonymous pipes because you do not have an anchor URL for it. Now, named pipes which have an URL with them are much more powerful. They can have bidirectional communication on single file descriptor. No parent-child relationship is needed, and it's available both on Unix and Windows. This part we are going to skip. So let me quickly come to the demo of pipes in case of Unix example. So the code again is from the textbook. I think I have just tweaked it a little bit by adding a sleep somewhere, if I'm not wrong. Yeah. So here I have changed some of the code. This is to make sure that we are able to attach debuggers and other things to running process. Again, many a times when we fork, we have a challenge. Should the child be debugged or the parent be debugged? Default behavior is GDB continues with the parent. We can also switch to the child, but then it becomes difficult. Another option is you continue to run and debug parent in one window while you attach to the child in another window and still debug it. So that is what we will demonstrate as this code execution. These modified files we will make sure are made available to you by end of the session. Okay, so I think rest of the code is as before. So on the two windows, I will start off with so I will leave this to debug our child instance. I will use this larger font size to actually debug and run. Okay, so for us, most of the interesting things will happen after 34. So let us break at 34. Now we can do a next, which means we have created the child. As a parent, the child ID is 3235. I can come to the other window and say attach. Remember, I am debugging the same binary. In this window, I ran it. In this window, I am attaching to it. Okay. I will have to do a sudo to attach to it. Sorry. Okay, so we have been able to attach to it. It is going to go through a sleep of 30 seconds. I hope it has not completed it. So let us list it once more. Let us put a breakpoint at 41. And here we will go with the next step. As a parent, we will get the child PID which is greater than 0. So we end up printing these things. I have already done this part, so we don't have to worry. Okay, we have to actually look at breaking at 49. We have broken at 41. So let me add break 49 as well. The next instruction is this is going to sleep for 30 seconds. We can let that happen. Out here, we can let it continue to run. So as it sleeps, it should come out and hit either line 41 or 49 depending on the code logic we have. So 41 was for parent, 49 is for both, so we should hit 49 in this case. I am still continuing to step through the server end. I am going to write the message now. As soon as I wrote the message, on the other end, it was already waiting for the read, and that is what has happened. The read has completed and we have sort of terminated. So I could not do it within the 30-second buffer I had on the client side. I will repeat the demo once and see if we can get the proper output. Now the output interestingly comes on this window. Why does the output come here? Where we were running the parent? Remember, the execution for both parent and child were launched on this terminal. So even though debug is happening from this, the output and input will continue to happen from this terminal. That's why we are seeing output coming here. Let me complete this and quit. We will run it once more. From here and resume with sudo. Let's see the breakpoints. We will break at 34, or rather later. Break at 34 is fine for us. Run. Next, int PID. Attach 1. So I put a breakpoint now. Hopefully this time we will catch it because we are still within the sleep. Backtrace is how we can see where we are. So we are on Unix pipeline 46. This sleep, we are still executing that sleep, so we should be fine. On the server side, I will say next. The sleep starts on the server side as well. Here we have already put a breakpoint, so we can just say continue. So it came to line 49. If I list it, 49 is for the parent, and again this is where 49 is. So if I do next, the if condition will be false. I come to line 61. List it again. So after 53 it is listing 56 till 65. This is what we do. 61 is where we are closing the right end and then going to read this message. This read will be a blocking read. If you remember synchronous and blocking. So right now we are going to enter into a blocking read here. Similarly, on the producer parent, I do next. It's closing the read end, and as soon as it writes, you will notice this part will come out. So I will do a step to the next. The write has completed. We will not worry about close right now. So we completed the read, which was a synchronous call, and now we are going to print it. So the moment we do the printf, the message comes out here. And then you can continue till termination for both ends for processing to complete. So again, parent child, the child created through fork, and then we later attached through GDB is what we demonstrated. By stepping through the code, we could also understand the flow of code, how the write is unblocking the read, and so forth. I hope this also clarifies the synchronous and asynchronous calls with respect to buffering and all that we had discussed in the theory part before the break. Any question for the pipe? Again, I will make sure the modified code is with you for you to attach the debugger and play with it. Okay, if there are no questions, let us get to the interesting part now, which is the last thing we wanted to have as part of our discussion on OS. As I said, sockets and remote procedure calls and so forth are getting more to networks, should be covered tomorrow. We have already done GDB, sorry, this thing I had missed. So let us look at strace, another debug tool, which can be used to look at what are the system calls being made in our applications. So while debugging is more intrusive, it does sort of needing you to run code that is compiled with debug enabled. Unless you have GCC with -G enabled, it will not have those symbols to debug the code. Remember, in the make file, I had shown you that you would have to have either G3 or GGDB and turn off optimizations to ensure we can debug the code. Many times we have binaries on which the debug code is not available, so we will need to look at system calls and what they are doing with system calls to get a hang of it. So let us do this as trace. We can pick any binary we want. So for now, I will just go with date, which is going to display the date to us. This will also demonstrate the discussion we had pre-lunch where Avijat discussed about dynamic linking, runtime loading, and so on. So what is happening internally is the moment we do strace, the shell, bash in our case, forks and does an exec VE for the binary which is implementing date, which is at location /bin/date. So before that, bash has also looked at the path and other environment variables to figure out what executable to run. The only argument is arg0, if you remember, in argc, argv perspective, date. And then there are 29 environmental variables that are getting passed to this child process, which is doing an exec VE. The first system call is break. This expands the memory, allocates memory basically. And then it's looking at the linkers specific config files under /etc. It doesn't find these two files, it finds the third file, which is ld.so.cache. And when it opens it with file descriptor 3. Then fstat on file descriptor 3 gets values of st size and other things, no errors there, followed by mmap. Most likely this mmap is for the same ld.so.cache file, file descriptor 3 here, file size 3 being used here, and so forth. Now you can start debugging what is happening with the binary. It's trying to first load into memory the content of ld.so.cache. And once it has loaded into memory, it closes the file descriptor, tries to open a few other files. Finally, it finds libc.so.6, which is the shared library for libc, the basic library that implements POSIX C calls. It gets it in this path and again opens it as file descriptor 3. Why is it getting file descriptor 3? Because we had closed it here, so it can reuse this descriptor again. It reads the format, and the format reads back the 832 bytes, starting with 177 as octal, I guess, and ELF as the file format. Then it does an fstat and it does an mmap. Fstat says the file is pretty huge, almost 1.8 MB. So post mmap, it will get it allocated at some location. So this is anonymous, followed by actually the file descriptor and so on. Memory is protected for modification. It will only execute. Read and execute is the only thing we do there because it's binary code. And then bunch of other things. Till somewhere here we get to local time as a format, followed by finally printing the date here. So these are the system calls that have happened just when we invoked the binary for date, right? If I change my time zone, so this is set to MDT, probably mid US time zone. So if I change my locale to be IST, let me try that. This will not help. So somewhere I can set it and then it will probably locale gen or something. It should convert to IST as well. We can look at few other commands. I will just do one more trace and let us just say echo. Let's do the output of cat / proc / CPU info or mem info. I think mem info is smaller. In this case, we will have a binary for cat and there will be other arguments being passed in. So if we look at it, the binary /bin /cat, the way we have executed is through cat. The first argument is, or arg C is set to 2 now, argv0 is cat, argv1 is proc mem info, 29 environment variables as before. And then it goes with rest of the similar stuff that we have looked at even with date. Out here it opens proc mem info, read only, does an fstat on it, maps it to memory, then reads the values, and then finally whatever it has read, 1251 bytes that were read, it will write it back. So that is the output we end up seeing, followed by memory and map and closing till we exit. So strace is our buddy to sort of reverse analyze or debug applications to which we do not have enough of debug symbols and variables available to us. The last part, the env part, where we had 29 variables. These are the environment variables that get passed on. So if I were to do env and pipe it to word count, that should be 29. These 29 variables are what is getting passed on as just a minute. Not local time. Out here. This 29 env variables. With me so far? Okay, so we can do similar stuff with other commands. I will leave this last part of exercise for you to try it out. Let us move to the bakery algorithm. First, see why it is needed, and then finally we look at multi-threaded example of bakery, and in that process we would also have okay, these are some notes of what I've already done with you guys, so you can use it from the slides for debugging. We are going to look at bakery with respect to multi-threaded applications, so some more aspects to look at from here. Now, this algorithm comes from one of the pioneers, I would say, with respect to algorithms in distributed as well as non-distributed applications. Leslie Lamport has done a lot of work on synchronization. The motivation is sort of coming from real world, where you have a baker serving multiple customers, and typically they will be busy serving customers, so they do not want to have the hassle of figuring out who will be served next. So they have put a small machine on which tokens are being dispensed in serial numbers, one after the other. Now, only thing is, when you convert from a physical world with a baker and tokens being issued by a machine to a cyber world, where sort of customers are the processes or threads. In physical world, if only one person can enter at a time, sequential number can be given. We have a global view or a global variable that can be incremented without having an issue. But in cyber world, with multi-core systems and so forth, parallelly two processes can end up accessing the same variable or the same machine which is issuing token and get the same number. So given that there is no way of avoiding or implementing mutual exclusion, how can we still achieve this is what bakery algorithm targets. So what it ends up doing is it ends up having a global variable which will be incremented, so monotonically increasing number. And there is a chance that because of multi-core system, two processes or two threads simultaneously, I would keep it as threads, two threads simultaneously get the same number, in which case there would be a tiebreaker that would be used. A typical tiebreaker would be the process ID or a thread ID that is associated with the requesting entity. So again, flipping it back to the real world, it could be your social security number in US perspective or Aadhaar number in India's perspective, used as a tiebreaker. Now, process ID or a thread ID would be unique with respect to a given system. But when we get towards distributed system, can we still get some unique values in similar manner? Any thoughts? How will we break ties? If we are, again, I'm setting you up for tomorrow, so I'm just trying to get some responses from you as to how we can look at tie breaks if same number is being shown by two different processes running on two different machines, for example. Any thoughts?
You could look at the timestamps, right?
Okay, looks like again I am losing you guys. So there have been attempts to use MAC addresses or IP addresses along with process IDs and other things, but now with virtualization and similar approaches, even the MAC may be same, even the IP addresses may be same, and so on. So if we have to go beyond one system, we have to get into a class of algorithms that deal with distributed consensus. We start talking of things like Byzantine faults and so forth. So those will be some motivations to go there. Now quickly I am moving into a single machine multi-threaded demo. The code for this demo is coming from Geeks for Geeks. Some of you may have already seen it. So again, a little bit tweak on it. So this has to be multi-threaded, so pthread would be there, and now member is a macro which tries to ensure buffer synchronization does happen. It does not do a mutual exclusion, but it does make sure that memory and other things we are sort of not having too much of a clash. Then it goes ahead and looks at a ticketing mechanism, and this, remember, is a multi-threaded system, which means the global variables, these three variables rather, tickets, choosing, and resources are available to all the threads. We are going to run 8 threads in all. Global variables have been marked volatile, so calls like sync, synchronize, and all will try to protect the code execution with respect to these variables. There is an aspect which takes a lock in code logic. I will skip it for now. We will come back and look at it. Then there is an unlock which just releases the ticket thread, setting it to 0. Use resource. This is the critical section we want to protect. So through lock unlock, we are protecting this critical section. Some basic printouts with respect to resource usage. They are saying we are using the resource for 2 minutes and then releasing the resource. So this is again an update to a global variable, though we are not protecting it at this point. Out here, sorry, this should be the other way around. Sorry about this. Sleep should have preceded that. Now in POSIX thread, when we start a thread, it is supposed to have a body similar to the way we go with main as the body of an executable. POSIX thread has a signature of void star as the return and void star as the argument, and it can be internally typecasted the way we want. For ease of debugging, again we have inserted some sleep here. We lock with our thread ID, that is the argument being passed to us. We use the resource and then unlock. That is how we are going with. We are not using mutex and semaphore, but still this algorithm helps us achieve the goals. As far as main is concerned, we are just initializing the global variables, setting them to null. Then we are creating the threads, and all 8 threads get created. Basic housekeeping of printing the thread ID. This is not a must. And then we sit in a loop and wait for the threads to terminate. Once the threads terminate, exits, returns with 0. So the code logic is in a reverse order. Let me make sure this line indentation is easy. Hope this fits the screen now for you to look at me. So this is our main. Setting up or cleaning up our global variables, initializing them to 0. Then having a local variable in main for threads. This is pthread is a data structure to hold the thread ID internally created by pthread library. We create those threads. We are printing the thread ID, but it doesn't help much because these are internal to the library. These are not kernel specific. And then finally we leave the resources. This is waiting for the threads to terminate. So I'm going to do a couple of changes. Rather than running with request count as 10, I will run it with request count of just 5. Rather than the thread count of 8, I will run it with thread count of 4. This is keeping us in control with respect to the output we generate. And once we are done with the execution, we will come back and look at the logic of lock and unlock. Unlock is simple, but lock is the one that helps get the protection for us. Okay, so for the purpose of debugging multi-threaded algorithms, we need to use thread specific calls. iThreads gives us the details of the threads that are active, and then we can select a thread to debug and so forth. So if you do not want other threads to stop, we can use set pagination off and set non-stop as on. So other threads will run while we are debugging one thread. These are some of the thread specific stuff to look at as we go further. Okay, so let us break at 120. Run. Now at this point, I feel that after we have created the threads, there is a 30-second sleep in the body of the thread. So we can put a breakpoint at 135. So if I say continue now, it will create the 4 threads. I can say info on threads, and then I can say thread 3, and I will have to say set non-stop on. Okay, so if I'm looking at set thread 3, which is a lightweight process created by POSIX threads library. The main is running as 3375, 3379 to 3382 are the other 4 threads created here. Right now I am on line number 107 of bakery.c. I will open it in the other terminal. So I'm still on sleep. Another thing we can do is ls/proc/ what was the process ID for our main thread? 3375. So it will mention that these are the other threads created by 3375. Another way to look at it. PSP 3375 also gives some details saying it has got 4 threads running under it and so forth. Now once the sleep completes, we will have to run the threads. So we will continue running, and then once the sleep completes, we will start seeing resources being used. So thread 3 is actually 01. I think it will be 2. Let's see what happens. Sorry, I have not put a breakpoint yet. I will let it continue for now. I will repeat this experiment once more. So I forgot to put a breakpoint. There has to be an additional breakpoint added. So what has happened is, in the very beginning, 0, 1 and 2 have continued to use resources, and towards the end 3 used the resources. Probably because I had attached to it, but I had not put a breakpoint. I will run it again, and this time I will also put a breakpoint, and the breakpoint we will put would be at say 95. No, this is not correct.
Abhishek, sorry to interrupt. How much content for this session is remaining now?
Sorry, ma'am, can you repeat that?
How much content of this session is remaining, because we are supposed to break at 4:30 as per the schedule.
Another 10 minutes, I think we will be done. So
Okay,
let us
okay.
finish by 4:45.
All right, all right.
Let me quit and come back once more. So GDB bakery, we will quickly repeat the commands we have done last time. We will continue once more. Threads are created. Now attach, or we will sort of look at thread, specific thread, which is, let us say, thread 2 now. I won't go to thread 3. I will go to thread, okay. Threads. So this would be actually 0 in our context. 1, 2, 3. We are running 4 threads. So I will say thread 3, and then we say continue again. So 3422 is the lightweight process that we are continuing with. Looks like I have not been able to latch onto the thread right now. So thread 2 I could catch up with 3421 as the ID. It is still in sleep. And now I can do continue on this thread. So thread 3 has hit breakpoint 2 of use resource, which is the sleep come at 2. If I do a backtrace, it will tell. So thread 3 is now executing on this. I can remove all the breakpoints and let it continue to run. But I just wanted to make sure other threads are ahead of this thread with respect to execution. So I will give it another minute and then let it run. So in this demo, there is some references that will change between what GDB puts as thread 0. Actually, GDB never uses thread 0. It starts from 1. Versus what is our indexing? Our indexing is 0, 1, 2, 3 in the code, while GDB is indexing as thread 1 as the main thread, followed by 2, 3, 4, and 5. That's why we will have some differences across them. So this is an example of multiple threads being created, and then they are using the resource, sort of sleeping on the resource for 2 seconds and so forth. So now I will come back and look at how the lock logic is implemented to ensure that we are not having a simultaneous usage by resource from two different threads. Sorry about processes. Two different threads. Lock is the primary implementation that enables it. So at the very beginning, we come in and set this variable. Remember, there are 3 global variables, 2 as arrays and 1 as the actual resource being used. And combination of these 3 are going to help us ensure that we are locking in a proper manner with the tiebreaker implementation added in there. So for our thread ID, we will put that we are choosing the resource right now. We sync up on the memory. Then we are looking at who is holding the maximum ticket. Our ticket ID has to be maximum ticket plus 1. So we go through all the threads. check the ticket ID, and if the ticket ID is less than max, the max ticket ID is updated. And then we are going to put ourselves as max ticket ID plus 1. So this way we first attempt to make sure that this ticket ID is continuously increasing. There is a rare case that two processes simultaneously execute this part of the code and they end up with the same ticket ID. Two threads simultaneously execute and end up with the same ticket ID. So that is where we will end up having the tiebreaker. So once we have identified our own ticket ID, this variable where we had said we are choosing thread, we will set it to 0. Now we are looking at figuring out who should be getting the next resource access, sort of. So for all the threads, each of the threads will run this piece of code. They have to make sure others are, if others are choosing, we are waiting on it. So we want to wait till we have seen that everybody else is stopped choosing. So it's likely that one or two of the nodes are still running this part. We will wait for them to come out. So this piece of logic makes sure of that if others are choosing, in this loop we are making sure that we wait for them to come out of choosing. Then we compare if ticket of other is non-zero and less than our ticket, let us make it more readable. So we are looking at two criteria. First thing is the other thread's ticket should be non-zero, and once it is non-zero, we are comparing is the other's ticket smaller than ours or equal to ours, and then based on that, finally we are looking at if they are equal, then is the other's process ID or thread ID smaller than ours, in which case the other thread is winner. We are not going to get the resource. I will repeat it again. This is not coming out right, so I will slightly indent it in a manner that you can understand it better. So let us start with this part. So here we are looking at, do we have a tie? If some other thread has got same ticket count as us, which means there is a tie. In that case, if the other thread's thread ID is smaller than ours, they are the winner. So this is covering the OR part here. Tie and its resolution. There is a chance that the other thread already is holding a lower ticket. So they have walked in before us in the bakery, so they will get served first. Not a problem at all. So they take the service. In that case, assuming the other thread is non-zero, yeah, obviously if somebody is not having a ticket, they cannot get service. So that is the first criteria, and then followed by these two criteria. If these two hold, that means I as a thread should not get served, so I will not do anything. That is what some indentation issue, but that should be fine. So this is where we make sure that we come out of this loop only when my thread ID is lower than everybody else. And that is when I have acquired the lock. So if my my ticket ID is lower than everybody else, I am the next one to be serviced. So that is how I have acquired the lock. As part of unlock, I will just put my ticket as disposed. I am not having the ticket anymore, so my ticket is set as 0, which means For anybody else, they will know that I don't have a token, so they don't wait on me. They only compare among the people who have token values as non-zero or ticket values as non-zero. So the logic of works and ensures that only one thread at a time is getting serviced. Now, few things about this implementation. It works only when there are no faults in the system. The algorithm is behaving as expected and everybody is running in a trustworthy environment. If there are Byzantine faults or malicious entities that starts getting into a different set of problems, the bakery algorithm doesn't solve that. Few of you who are inclined to look at next level of synchronization again across machines, it gets into remote direct memory access and so forth. You are welcome to look at it.